चलो सब लोग आगे शुरू कर लें. About 37-40 people have come. Very good. So, we wanted to talk about instability of structures, right? So now, stability of structures is fundamentally taken in two ways. One is local buckling and one is global buckling. Is making sense?
No, sir.
No. Okay. Brilliant. Didn't make sense to me also. So I was wondering whether it makes sense to anybody. कोई member है, ठीक है? See, instability is a geometric problem. Okay, are we okay with this?
Geometric problem in the sense
it's a problem based upon the geometry of the structure.
Okay.
Okay. And in your solid, I don't think solid mechanics में तुमने किया होगा, but structural analysis 2 का course तुम लोगों ने किया है?
Yes, sir.
अच्छा, उसके अंदर तुमने geometric stiffness matrix करके कोई एक concept देखा था?
Yes, sir, but don't remember it very well.
Okay. So the thing is that, see, how is your stiffness matrix generated? Your stiffness matrix is generated through virtual work equation. Is this okay?
Yes, sir.
Okay. Now this virtual work is fundamentally looking at what is the work done. Okay. By so what you take is that you take a pin supported beam. Okay. And then you have the flexibility matrix of this pin supported beam, which is what is the force needed for unit deformation. Is that okay? So in some sense, a series of forces which are needed for a set of virtual deformations is your flexibility matrix. Okay.
Yes.
And the series of displacements which are needed for unit forces ends up as becoming your stiffness matrix.
Yes, sir.
यहाँ तक ठीक है? यहाँ तक I think are we on the same page? And what you end up getting is an external virtual work and an internal virtual work. Okay. So the internal virtual work generates your stiffness matrix and your external virtual works generate your force matrix. And equate the two, which is that you're saying that the net virtual work of the system is 0. And you end up getting a series of equations, which is K times K is your stiffness matrix and X, which is your individual displacements, is equal to F, which is your external virtual work system. Are we good with this?
Yes, sir.
So the statement we are making is that your internal work is equal to your external virtual work. Okay. Now, when you have actual forces in members, in addition to the virtual work, which is done by your rotations and displacements at your ends, which are your flexural rotations and displacements, you also end up getting a virtual work component, which is because of your force and the displacement of a member in the lateral direction because of that force. Is that okay?
Yes, sir.
Okay, so let me open up kind of a paint screen so that I can do a little bit of drawing. I love doing this. Okay, now this is your member, and there is some kind of a force is acting on this. This member ends up becoming light. So,
sir, you have not shared your screen.
Oh, I have not shared my screen. Oh, brilliant. How does one share screen? One goes there and share screens. Okay, there you go. Can you see my screen now?
Yes, sir.
Okay, so basically you and I'm saying that you have some number which has some forces which are acting on it. Is cool. Now, and supposing you have got some rotation, which is some flexure, which is also acting on. So this member bends like this because of flexure. And this displacement generates a work which is P times delta. Are we okay with this?
Yes, sir.
Okay. Now this P delta term, which you're getting, this is your geometric stiffness term. Because why is it called the geometric stiffness? Because it is fundamentally dependent upon the geometry of the structure. Okay. Now, ये जो displacement हो रहा है आपका, now this displacement can happen because of flexure, or it can also happen because of a sway. So if this building sways like this, and then you have got some force there, okay. Now this force multiplied by this delta will also generate some kind of virtual work system. Is this also making sense? I'm not going to get into actual derivations. I'm just trying to conceptually explain what is instability for structure. Is this making sense? This P delta kind of a thing which is happening?
Yes, sir.
Okay. Now this is why it is called a P delta effect. And why is it a P delta? Because in a particular member, it is just, this is what is your local buckling. Okay. And why is it called a local buckling? Because this is your stiffness matrix, which is only dependent upon the member itself. Is this fine? That's why this is called a local buckling. Are we good with this? This is a global buckling because it is not the local member which is buckling, but the sway of structure which is generating this addition. The sway is generating.
So your screen is still when you wrote P delta. After that, the screen didn't move.
Oh, I don't know what is happening then. Should I share it again?
Yes, sir.
Are you seeing the screen now?
It's blank, sir.
The screen is blank,
Hello.
is it? Hello.
Sir, I think the problem with is with him only. Since I am saying whatever you are writing.
Oh,
Okay. That's on my end. Sorry.
Okay, so it might just be some kind of a bandwidth problem with you here.
Yes, sir.
Okay. Okay. So can you see the screen and see what I'm writing?
Yes, sir.
Yes, sir.
Yes, sir. Yes.
So there is a local buckling which happens because of the sway of the member itself, and a global buckling which is happening because of the sway of the structure. Is this making sense? Now, what you end up getting, so now let me just get a new page because I think this one is kind of done. Or I can just erase everything. How does one erase everything? Why do I want to erase? I can just select everything and delete. Yeah, fantastic. Now, are we good with this? Now you're seeing a blank screen again. So, if I have a structure, what is happening now? I need to go to a pencil. Yeah. So now, if I see this structure, and yeah, I think this is better. If I see this structure and I say that this is a kind of a structure which exists, which has these vertical loads, and you have got these lateral loads, this structure is going to deform in some kind of a way like that. Are we okay with this? So you'll have these forces here. Now, each of these forces has actually shifted a delta value out here. Is this making sense? Because of this shift, there is another term which is coming in your virtual work equation, which is some P matrix times your delta matrix. And this ends up as becoming your geometric stiffness. And your actual stiffness is K elastic, which is your elastic stiffness that I talked about earlier, minus your geometric stiffness. This is the actual stiffness of the structure. I derive how a geometric matrix like, and I can put it together in some kind of a. But as of now, can we just take it as something which is acceptable? That this is your actual stiffness of the structure. Is this making sense? I mean, at least conceptual way, is this making sense? What I'm trying to say is that your stiffness matrix is a virtual work equation. There is a virtual work coming because of pressure, and there is actual work coming because of your sway. So the flexible virtual work is what is elastic stiffness, and your sway virtual work is your geometric stiffness, and Ke minus Kg ends up as becoming your effective stiffness. So your actual stiffness of your structure is not the elastic stiffness with which you use mechanics mostly. The actual stiffness of your structure is the elastic stiffness minus the geometric stiffness. Does this make sense, guys?
Yes, sir.
Okay. Now, whenever this Ke minus Kg will end up becoming 0, you will get points of what do you call it, instability. And why it a point of instability? Because if there is a 0 stiffness, for a minimum force, you'll get an infinite movement. Okay, so these ends up as becoming your points of instability. And if you're looking at the structural instability, your structural instability is whenever your effective stiffness becomes 0. Now, if you look at it, you will end up getting, again, now let me again select and remove it. And say that what you'll end up getting is your stiffness matrix will end up looking like some K11, K22, dot, 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 KNN, K12, K21 times delta 1, delta 2, delta n is equal to F1, F2, Fn. Do you remember a equation which looks something like this? In your structural mechanics? Yeah. Now, what do you mean? So basically, if any of these general terms end up becoming 0, so that means that becomes 0. This ends up as being an instability, which is related to this degree of freedom. Is this making sense, guys?
Sir, once more. The last when you explained.
Okay. So supposing this term becomes 0, this term is related to this degree of freedom. So this term becoming 0. See, this when we say their matrix is equal to 0, you say a matrix is equal to 0 whenever the determinant of the matrix okay, is equal to 0. Is this
Yes,
making
sir.
sense? Now, if any of your diagonal end up becoming 0, your matrix determinant will become 0. Is this also cool?
Mm, no, sir.
Okay. So supposing you have a mix, which is 2, 1, 1, 0. Okay. You will always end up getting that the whatever your determinant is either 0 or less than 0.
Yes, sir. It would be less than
What?
0.
Forget all this. What is the rank of that matrix, man? So, so when you put up a matrix, what is the rank of the matrix? The rank of the matrix is the independent rows or columns. Is this cool?
Yes, sir.
Is this the rank of the matrix? So if you have a matrix which is K, K is invertible only when the rank of K is equal to N. Is this also cool?
Yes, sir.
Now, if the rank of K becomes, instead of N, it becomes N minus 1, it becomes a non-invertible matrix.
Yes, sir.
And what do you mean by non-invertible matrix? You mean that the determinant of the matrix is 0. Because
Yes, sir.
what is the inverse of a matrix? The inverse of the matrix is something which is then divided by the determinant of the matrix. If the determinant of the matrix is 0, it means that it is a non-invertible matrix.
Yes, sir.
ठीक है? Mathematics याद है? Algebra याद है?
Yes, sir. Yes, sir.
ये ठीक है ना मैं कह रहा हूँ जो? Is this making sense?
Yes, sir.
So now what you are ending up getting whenever any of your diagonal terms ends up becoming 0, what you end up getting is a non-invertible matrix. Okay. In how many ways can this end up becoming 0? This can end up becoming 0 in n ways, because it could be this term which becomes 0, it could be this term which becomes 0, it could be this term which becomes 0. So these are the n different ways in which your matrix can become.
Yes, sir.
Are we good with this till now?
Yes, sir.
Fantastic. Now, your Kg, which is your geometric swiftness matrix, is dependent upon what is your axial force P. Are we okay with this?
Yes, sir.
Okay. Now, when it is dependent upon axial force P, for this term to become 0, then there will be some set of P force which will turn this 0. Are we okay?
Yes, sir.
Now there will be some other set of P forces which will turn this 0. Are we okay with this?
Yes, sir.
Now, so the lowest magnitude of P ends up as becoming your first buckling shape. Are we good with this? The second
Okay,
one
sir.
will give you your second shape. Are we good with this? And the nth one will give you your nth shape. Is this making sense?
Yes, sir.
Now, whenever any of these shapes, any of these sets of forces generate a system Kg, which makes the K effective 0, okay, but does not generate a local buckling. This is called, how does one put it? One is a local buckling. What was the term we used? One was a local buckling and one was a global buckling. Yeah. Whenever kg becomes 0, makes k effective 0 without generating a local buckling shape, it will make this a global buckling problem. Okay. On the other hand, if at this level of forces, your individual members buckle, it ends up as becoming a local buckling problem. Is this again making sense?
Okay. So we are actually
दो
saying,
तरीके से बकल होता है ना कि ये P है, ये P से ये इंडिविजुअल मेंबर बकल होगा. ये तो हमने अभी ऑलरेडी बात कर ली है पिछले लेक्चर में.
yes sir.
बट ये बकलिंग होने के पहले अगर ग्लोबल बकलिंग हो जाए तो वो एक ग्लोबल इंस्टेबिलिटी ऑफ अ स्ट्रक्चर जनरेट हो रही है. That your individual local members are not buckling, your overall structure is buckling.
Yes sir.
Okay, that's the only thing that you have to worry about. And why is that the only thing that you worry about? Because if the global buckling happens after the member buckling, so your member has already failed here.
Yes sir.
You get my point. Now, the point here is that there are two things that we can take a look at. Okay, just a minute. Let me just again clear this and go back to my brush. Yeah. There are two things we can look at. You're looking at buckling. And you're saying that there are two forms which can happen. One is global and one is local. Are we good with this till now?
Yes sir.
Local is something that we have already talked about. And this is nothing but P has to be less than pi squared E divided by L by R squared. Pi squared EA, sorry. Is this okay? This is what we have already talked about.
Yes sir.
Now, supposing at P, so let me call this P1, and at P2 is less P1 if global buckling happens, then P2 ends up as becoming critical. However, if P2 is greater than P1, global buckling is not a problem because यार तुम्हारा structure तो locally already buckle हो चुका है ना.
Yes sir.
So this is what you mean by the structural instability. Is this making sense?
Yes sir.
Brilliant. So now this has made sense to me also, so I can say that हाँ तुमको भी it should make sense. Chalo, very good. So does this solve the question that you have about instability, or is there something more that you'd like to talk about?
I think it's okay sir.
Brilliant. तो ये हो गया. So now let us go to, I don't want to save this. No. And now let's go to, कहाँ गया अभी मेरा PowerPoint? नहीं खुला है क्या? हाँ खुला है यार, ये तो देखो PowerPoint तो खुला है. यहाँ पे शेयर वाले ऑप्शन में क्यों नहीं आ रहा? हाँ ये रहा. Can you see the screen now? So now let's go to beam design. These are the different types of steel beams which can exist. Just take a look at it. You can have a solid section, which is, you can have a solid section, You can have a roll channel section. You can have a open section. You can have a built-up section. You can have a thin-walled section, a compound section. You can have a composite beam where this is steel and this is concrete, and you have got this is your shear connector, which is ensuring that the system behaves in a homogeneous way. You can have an encased beam. You can take a I-beam, cut it like this, reverse it, and get a tapered section. And you can be also very, very innovative, where you can do this kind of a cut, open it and shift it so that this kind of a system. Now, of course, the difference here, and I think this is slightly wrong, is this beam actually ends up as becoming this with this kind of a section in place. So the depth increases. Because इसको तुम shift करके ऊपर ले जा रहे हो ना, तो तुम उसको ऊपर you're diagonal. So this line will become here. So basically this much h will be the increase in the depth of the beam. So you can have beams like this. Is this making sense? Is this okay?
Yes, sir.
And you can get types of beams in the span. So if you've got 3 to 6 meters, you can use angles, and it is used for these things. If you have a rolled section, it is used for these things. A castellated beam, so that beam is called a castellated beam. So this is a open space. Is used for long span light loads. Then you have plate girders for bridges and things like that. Plate girders are basically built up sections which are like that. So, and just all steels, that ends up as becoming a plate girder. Box girders can be used for this. Open web joists can be used for something. Trusses can be used for something else. And these are the kind of spans that these are typically used for. Is this okay?
Yes, sir.
Then you have got hot roll beams. Now, what are the main failures of beam? One is excessive bend, which means that either your sigma T or your sigma C reaches yield. And another is instability, which is that you end up getting a buckling in that direction. That so this actually what happens is that when you have a beam, this ends up as becoming a compression flange. The compression flange can be thought about as a column that it's a member which has an axial load, and there is a flexure. So you can end up getting a lateral instability because of that. Of course, we'll calculate how you can work that out in the later part of this course, but you can understand this, that your beam can, because of your compression here, this flange can buckle. Is this making sense? So you had a column and you could end up getting this kind of a buckling happening because of compression load. Now, if you turn this around, you'll end up getting a beam which can end up having this kind of a buckling happening because of that kind of a force system. Is this making sense?
Yes, sir.
Then you can have failure by local buckling of a flange or local wing of a shear of a web because of shear. So you can end up getting, that was a global buckling where the entire beam had buckled. Another is that you can have a box section, and the box section top, which is under compression, that can buckle, which can give you some kind of a local buckling problem. You can have a beam with a web, and the web is under shear, and this can buckle because of that. So either your local plate buckling or your local buckling here, the local buckling section. And you can have a shear yield of your web, you can have a crushing of the web, you can have buckling of thin flanges. So these are the different forms of failures which exist in beams. Of course, we are just listing all of these here for mm, due diligence, but in this course, we are not going to be concentrating on all of this. We're just going to be concentrating on some regular steel structures. So stability of beams. So when Rajiv had talked about stability, is it stability of beams that he had talked about or stability of structures that he had talked about?
He just told about to ask about stability and instability of all the structures, I
Okay,
suppose.
so fantastic. So that I've talked to you about. So I think okay. So now when we get into stability of beams, anything which buckles will generate an instability. Uh, you can get a laterally deflected shape of the beam. So the beam is like this. Before buckling, it is moving just in its own axis. And after buckling, it kind of moves in some kind of a theta away from its own axis. Is this making sense?
Yes, sir.
And there's a similarity of column and beam buckling, which is what we had talked about. That column buckling is EA by L has to be greater than EI by L cubed. And for beam buckling, EIZ has to be greater than EIY. So, and what does this mean? So this means that your stiffness in this direction, which is EI by L cubed, has to be less than EA by L, which is the axial stiffness. Otherwise, what will happen? That your beam will crush before it buckles. And the other one, EIY, which is has to be less than EIZ. Otherwise, the beam will fail before it buckles. Is this making sense? That in buckling, you're always saying that in this direction, the section is weaker than in that direction. Similarly, in column buckling, in this direction, the structure is stronger than in that direction. Is this making sense? Hello?
Yes, sir.
It's making sense, right? That in a
Yes.
column, this direction is your strong direction, and that is your weaker direction for buckling to happen. In beams, this is your stronger direction, and that is your weaker direction, again for buckling to occur. And then you have a lateral torsional buckling, which is, so you have a twist. So this twist is generating your torsion. So why is it called lateral torsional buckling? Because lateral buckling is accompanied by a twist. And therefore it is called a lateral torsional buckling. Is this making sense, guys?
Yes, sir.
Just a minute, somebody else coming to bother me. Chalo, ho gaya. So you have different case studies. तो यहाँ तक ठीक है क्या? कितने बजे? What's the time? 3:40. Yeah. Okay. So are we good till here? Because I'm going to stop here because we have actually covered a lot. So I don't want to add into this right now. Are we good till here?
Yes, sir.
Hello, are we good till here?
Yes, sir.
Okay, any questions till now? Because today we have talked about, in concept, the different forms of buckling. We have talked about the instability of buildings. So I think that itself is a lot to cover in one class. So I'm going to stop now and ask if there are any questions that you have on what we have talked about till now. Or is it cool? Kirat Kaur,
Yes, sir.
is it okay? Have you understood what we have talked about today?
Yes, sir. We'll probably have to read this once to have a clearer idea, but it's good for a start.
Okay, brilliant. Thank you very much. Rahul Gupta, what do you think? Are you okay with this?
Yes, sir. Probably would have to read about geometric stiffness again.
Okay.
Open
But see, forget about the equations. In principle, have you understood what we have talked about today?
Yes, sir.
Okay. Was there to ask?
No, sir. It's clear for me.
Okay, brilliant. Thank you, everybody. I'll see you on Friday. Bye. Have a great Thursday, and I'll see you on Friday.